Hello students, once again you're welcome to Waidsum University. Without much ado, let's begin. Today our chapter is chapter 9, section 3, and the title of this chapter is Dynamic Routing Protocols. Dynamic Routing Protocols. So without much ado, let's begin. Now, first of all, what is a dynamic routing protocol? Okay, what is a dynamic routing protocol? A dynamic routing protocol uses multiple algorithms and different protocols to propagate the routing tables throughout the network to neighboring routers. Okay, so a dynamic, or like static routing protocol. You know, in the case of static routing protocol, the network administrator has to manually configure the route, the next route. But for dynamic routing protocol, the routing tables or routing informations or entries are automatically, that's what we mean by dynamically. They are automatically propagated, okay, through the network for all the routers to gain access to these routing table informations. Is that okay? So this is what we mean by dynamic routing protocol. This is what we mean by dynamic routing protocol. The most popular or the most common types of dynamic routing protocols include the routing information protocol, the RIP, the routing information protocol, although some texts call it routing Ethernet protocol. Okay, some texts call it routing Ethernet protocol, but specifically called routing information protocol. Okay, so this is one of the most common dynamic routing protocol, the routing information protocol, RIP. And another common one is the open shortest path first routing protocol. Open shortest path first routing protocols. These are very famous types of dynamic routing protocol. However, dynamic routing protocols are divided broadly into two categories. They're divided broadly into two categories. One is the distant vector routing protocol, and the second one is the link state routing protocol. The distance vector routing protocols and the link state routing protocols are further divided into all this RIP, OSPF, that's the open shortest path first routing protocol, the enhanced interior gateway routing protocol, the Broadway gateway routing protocol, and so on and so forth. Borderline gateway routing protocol, and so on and so forth. Okay, so these are the types of dynamic routing protocol that we might be looking at. Is that okay? So dynamic routing protocol includes, like we said, the open shortest path first routing protocol, and this one is a very famous one. Okay, it's a very famous type of dynamic routing protocol, and is being used in today's world. This open shortest path first routing protocol is very in use in today's world. Then another famous one is the EIGROP, that's enhanced interior gateway routing protocol. So the enhanced interior gateway routing protocol is considered a proprietary protocol for Cisco. Cisco is this is what Cisco uses. That's in a short form, the enhanced interior gateway routing protocol. This is Cisco's concept. This is Cisco's concept of routing protocol. Then again, we have RIP, other dynamic routing protocol. That's the routing information protocol. Okay, and then the fourth one, we have the border gateway routing protocol, BGP routing protocol. So these are the about 4 of these types in specific terms, but in broad terms, in a general category, we say there are 2 types. But simplifying it, we have subtypes. So the broad types are the distant vector routing protocol and the link state routing protocol. So we subdivide this, we get about 4 or more than this. The open shortest path first routing protocol. That's one. Then we have the enhanced ethereal gateway. We even have the ethereal gateway routing protocol before we had the enhanced interior gateway routing protocol, right? And then we have what we call the RIP routing protocols, the routing information protocol. And then before we have the border gateway routing protocol. So these are the four subsections of dynamic routing protocol. So now let's take a look at after we've in section 2, chapter 9, part 2, we studied the static routing protocol. We said the static routing protocol is a type of routing protocol where the network administrator has to manually enter the or manually configure the next route, the next hop count, okay, into the system. So in that case, it has its own limitation, right? Since you have to manually configure, it has its own limitation. From the modus of operandis, you already know that the static routing protocol has its own limitation. It's not dynamic, it's not flexible, it's not automatic. It's like manual car. Okay, the static routing protocol, for instance, is like manual because you have to manually enter the data, the routing table information, the routing entry into the system. Okay, you have to manually enter for your MAC address, for your PC, for everything. You have to manually key them in into the system. Okay, but unlike the dynamic routing protocol, the dynamic routing protocol, it doesn't have this limitation. Doesn't have this limitation. It has ability to propagate or ability to spread the routing table to the neighbor routers automatically to the neighbor, so that the system, the routing protocol, can determine the best route, for data packet to go through by looking at the traffic available in each of the routes. So dynamic routing protocol, it's for bigger network, for bigger like big campus network, or bigger environment, bigger organizations. Then the static route becomes a challenge, becomes a huge challenge. So hence we opt for dynamic routing protocol. So our observations so far from what we've learned in part 2, let's take a highlighter. It's our culture, so we can always show something. From what we have learned so far in part 2, we see the concept of configuring a network using a static route. That's what we did in section 2 of this. Configuring a network using a static route. Okay, just a moment. Okay, using a static route. Okay, so in part in section 2, what we did was we could figure out how we can do what we call configure the static route, right? That's what we did. How to configure the static route and the advantages that it has, and how this is done over a network. We've looked at this in section 2. But in section 3, we say no, we are not looking at the static route now, because in static route, like I said, it's like manual. Okay, you're configuring the routing yourself, right? You're doing it yourself. But in this path, we're not doing the routing ourselves. We go to use what we have. We go to route the information dynamically. The information is going to be routed dynamically. It's not going to be like done manually. It's like this is like automatic in case of that first comparison we made, or analogy that we made. For this analogy, this dynamic routing protocol seems where, or looks more like an automatic car. Okay, looks more like automatic car. So it became very obvious that the time required for entry and maintaining the static route was a problem in section 2. So we need to find a better ways to route our entry tables, our informations, and broadcast them through the router. So the maintaining and entry manually of this information into the routing table was a problem, okay, in the case of static route. Hence, the reason the static route protocol is of limited use in most of the campuses, in most of the big campuses. So the static route is of limited use. Okay, the static route is of limited use in most of the campus, or especially the big one. But for small organization, the static route is okay. It's okay. However, static routes are used in situations such as configuring small network. Yeah, small network routes we can easily blend with the static route. Now let's move on for dynamic route. So for today's work, we will focus on dynamic routing protocols, and we've already explained the meaning of dynamic routing protocol. Okay, we introduce what we call the dynamic routing protocol, which is an improvement. The dynamic routing protocol is an improvement over the static routing. Okay, it's an improvement, and this only uses what we call the dynamic. This system uses what we call the dynamic routing protocol that we're going to discuss in other subsections. However, let's look at dynamic as it were. Dynamic routing protocols enable the routers routing tables to be automatically, let's use the word automatically, updated to account for loss or changes in the route or changes in the data traffic. So a dynamic routing protocol enables the router's routing table. You know, every router has a routing table. We know this, right? A dynamic routing protocol enables the router's routing table to automatically, when need arise, when data packet needs to be sent, okay, automatically update the account it will update its account for any loss or for changes in the route or changes in the data traffic if it's broadcasted in the network. Okay, if any router broadcasts any data traffic or any message or anything regarding their routing table, all the neighboring routers will update this in their routing table. If a router A broadcasts its routing table over the entire network, all the routers will update their information in their routing table based on what has been broadcasted by router A. So router B, router C, router D, router E, they will all update their informations based on what they've received from A. Okay, because probably A wants to send a data packet, so it will broadcast its routing table to other routers, and those other routers will update their own information based on what router A has broadcasted. Okay, so they will update their information based on what router A has broadcasted. So as such, this one also has its own challenge, which we're going to look at later on. As such, a feedback will be obtained. So router A, we know the shortest path, the next hop to route is data packet through. Okay, the routers update their routing tables using the information obtained from the adjacent router. The adjacent router could be router A, okay, router B, router C could be adjacent router, and the information they receive from router A, they will update in their own routing table. The routing protocol is responsible for managing the exchange of routing information between the routers and the choice of the protocol defined. The choice of the protocol, the protocol that you use, you know, we've mentioned the different types, whether it's open shortest path first routing table, or whether it's RIP, routing information protocol, or whether it's enhanced interior gateway routing protocol, or whether it's border gateway routing protocol. Any of the routing protocol you choose will determine how the routing information is exchanged and used. How it is exchanged and how it is used is based on which of the routing protocol that you've chosen. Okay, how the information is obtained and how the information is put to use is dependent on the type of routing protocol that you've chosen, the type of dynamic routing protocol that we have chosen. So again, we say the routing protocol is responsible for managing and exchanging of routing information. The protocol you are using, the type of routing protocol you've chosen, is responsible for managing and exchanging the routing information between what? Between routers. Between routers. The type of routing protocol we've chosen, to be more specific, the type of dynamic routing protocol that we have chosen will be responsible, we determine and we manage and exchange, or the exchange of the routing information between routers. So if you choose open shortest path, that open shortest path has its own modus of operandis, and that itself determines what kind of information will be exchanged between routers, or how these informations will be exchanged between routers, especially on the how these informations will be exchanged between routers. And also we determine the choice of your routing. The choice of your routing is define how the routing information is exchanged and how it is used. So the choice you've made, like the type of the dynamic routing you've made or you've determined to use, will determine how your routing information will be exchanged and how it will be used. Is that okay? So let's move on. Now, table 9.2, features of dynamic routing protocols. Let's take a look at some of the features. I think this is supposed to be table 9.3. Okay, this is just a table 9.2. We've seen 9.1 before. Okay, now let's take a look at some features. Now, what information is exchanged between routers? These are the things like we want to look at to determine which type of dynamic routing protocol we're going to use. So first of all, you want to look what type of information you want to exchange between routers. This is some of the questions you need to ask yourself before you opt for which type of routing protocol you want to use. Okay, another is when is updated routing information exchanged? When? After the routers, the neighboring routers update their routing tables with the information they've received from the adjacent router, when will the information be exchanged? When will the updated routing information, will it be exchanged? Then another thing we need to ask before we determine what we're doing is what are the steps for reacting to changes in the network? What are the steps for reacting to changes in the network? What step do you need to take in order for maybe to react to the broadcast, to react to what the neighboring router has sent to the other routers? Then another question we need to know or ask or find a solution to in this section is we should be able to establish a criteria for establishing the best route selection. So we should formulate good criteria to help us select the best route that our data packet needs to go through. So if we're able to find answer to this, then we are good to go. Now let's take a look at these 4 key issues with dynamic routing protocols. 4 key issues with dynamic routing protocol. You know, like I said, it has its own challenges, it has its own challenges, and it has its own up and down. But let's take a look at the key issues with dynamic routing protocol. The first key issue is what we call the path determination. Because you know everything is automatic, it's not manual. You're not manually putting the values. So because as such, the path upon which the routing table information has to go, or the data packet has to go, the data packet specifically, or the traffic has to go, is dependent on ability of the routing table or the router to determine which path is available or is less traffic compared to others that the data packet that we're sending can go through. So path determination first, what it means is a procedure. What procedure is put in place? A procedure in the protocol that is used to determine the best route. A procedure in the protocol that is used to determine the best route. What procedure is put in place to determine the best route, meaning the best path to follow for the data packet to follow? What procedure do you have in place? What mechanism? Okay, you can use the word mechanism. What mechanism is put in place to determine the best route for the data packet to follow. Okay, that's what we mean by path determination. Path determination is the mechanism in place, put in place, the procedure mechanism that the protocol itself has, an algorithm, a procedural algorithm that the protocol itself, the developed protocol itself has, in order to determine the best path for data packet or for any routing entries to go. Then the second thing with key issues we need to look at in dynamic routing protocol is called the metric. Metric is very important because the metric helps us to select the best route from the best to the worst, helps us to get maybe itemize the routing options and notify or make us understand the best among all the options we have, ranking them, giving ranks to them from probably the best route to the worst route. So metric is actually the measure that is the measure assigned to routes for ranking the route best to worst. Okay, ranking. So when we say metric, what method we use to rank the routes? Because in a network, in a huge campus network, there are so many routers that are configured on the network. There are so many routers. So for a traffic or a data packet or a header that needs to be routed, what metrics are there to assign or to determine the best route for our data packet to go? Okay, because for all the routers that are available options, they have to be ranked so that we know which one is the best for our data packet to go, so that the data packet will not be in a traffic, will not be in a serious traffic. Okay, these are so in order to minimize redundancy, because we don't want a situation where some routers are free while some are super busy. They're so busy, the channels are busy, the routes are busy. Meanwhile, other routers are redundant. They're just sitting idle, not being used. So, any good routing protocol any good dynamic routing protocol should have the ability, the metric ability to determine the best route that is available to the worst one based on congestion. Based on congestion. If the route is busy, then it's probably one of the worst. If the route is free, then it's probably one of the best to send our data packet through. Is that okay? Okay. Now, the smaller the number, the better. Meaning, the smaller the available data packet that is going through a route, the better. Yeah, we've already explained this. Then, number 3 is convergence. Convergence is also a characteristic that needs to be considered when we are dealing with what we call the dynamic routing protocols. Okay, key issues that needs to be understood whenever we are dealing with dynamic routing protocols. This happens when a router obtains a clear view of the routes in network. Convergence, okay, a clear view, just like we studied convergent and divergent lenses in physics, right? Convergence, when you get a clear view of the routes that are available, all the routes that are available when a particular router that want to route gets a clear view of all the routers that are available in the network. Okay, when the clear view is obtained, then we say the router itself has a good side of convergence. Now, the time it takes for the router to obtain a clear view is called the convergence time. The time it takes is called the convergence time for a router to get a clear view of all the routes available on the network. The time it takes for the router to get a clear view of all the routes that are available on the network is called the convergence time. Okay, convergence itself is just happens when a router gets a clear view. Okay, we say the router has converged when it gets a clear view of all the routes in its network that is available on that particular network. Then we say it's convergent. But the time it takes it for it to get that clarity is called convergence time. Now, number 4, another thing to deal with in this concept is what we call the load balancing. What we call the load balancing. Okay, number 4. Another characteristics of dynamic routing protocol is load balancing. Yeah, we've talked about this. Some routes could be super busy while some routes are redundant. They're not doing anything. So in dynamic routing protocol, we want to avoid this. So any routing protocol that should be super in use, any dynamic routing protocol that should be super in use should be able to have these characteristics or an ability to balance load, not super congested traffic in some routes, and whereas in some other routes the traffics are free, the routes are free, they don't have anything going through them or passing through their way. So load balancing is a very key characteristic in dynamic routing protocol, because in dynamic you are not manually keen to say, okay, follow here or follow here or follow here. The system and algorithm, the routing system algorithm is able, with the use of this routing table, is able to obtain and determine which paths are good to go or are free for the system to go. Now, a procedure, so load balancing is a procedure in the protocol that enables router to use any of the multiple data paths. Okay, the procedure that a router has, or a capability that a router has to use any of the multiple data paths available from multiple routers to reach the destination, is called load balancing. So ability or capability that a router has, a procedural capability or mechanism in the algorithm of the routing protocols that enables a router to choose from the multiple data paths available to route the information from source to destination, is called load balancing. Okay, now let's move on. Let's take a look at examples of route metrics. Now, we've defined metrics already, that says that is the measure assigned to routes for ranking the routes from the best to the worst. Okay, now let's take a look at the examples of route metrics. So number 1 is hop count. Hop count is a good example of a route metrics. Okay, hop count is the number of routers that the data packet must pass through to reach the destination. Okay, to reach the destination network. It's actually the number of routers the data packet will go through. Before a data packet reaches a destination, probably sometimes it might pass through 2 routers or 3 routers or 4 or 5 or 6 or 10, depending on how large the network is. So your hop count is the number of routers you're going to pass through before you reach your destination as a data packet. Okay, the number of routers a data packet will pass through before that data packet reaches its destination. So this is a good example of metrics that we use in determining whether the dynamic routing protocol is a good one or not. Okay, you cannot leave a situation where you have only 2 routers or 1 router to reach your destination. You leave that option to go and be following option of 10 routers to reach a destination. So it means that's not a good metric. It's not a good metric of determination. The second one is reliability. The second case for metrics determination is reliability. Okay, reliability. Reliability is a measure of reliability of the link, typically in terms of the amount of errors. Okay, reliability. Let's put it in a very simple term, not just the way we've put it here. Reliability actually is the mean time before failure. The mean time, statistical mean, a statistical mean. So MEAN, the mean time before failure. Okay, is what we call reliability. What is the average number of time the data packet or the routing table that is broadcasted along the whole entire network we get to destination without errors, without error setting in, without failure. Okay, that's what we mean by reliability. The bandwidth has something to do with capacity, right? We already know bandwidth. Bandwidth is having to do with the data capacity, right? Data capacity of the networking link. Okay, a fast Ethernet 100 megabit. 100 megabit per second is actually speed. 100 megabit per second link has usually, the greater the speed, the greater the capacity, usually. So for 100 megabit per second link has a greater data capacity than a 10 megabit per second link. Okay, so this is the bigger the speed, the bigger the, or we can link speed in some cases to bandwidth. Okay, now delay is the time it takes for the data packet to travel from the source computers to the destination computer. So if it takes 5 microseconds, that's the delay time. If it takes 10, if it takes more, that's the delay, what we call delay. Delay is the time taken for the data packet to travel from your source to your destination. Cost is what the network administrator has determined, typically for a network, what it takes into account or what it spends on bandwidth and expenses of maintaining the network. That's what we call the cost. The cost is what the network administrator has taken into account for bandwidth, what he has spent on bandwidth and what he has spent in maintaining the bandwidth and every other thing that he has put in place to get the system up and running. Load has something to do with the network activities on a link or a router. The activity, how much of this data packet passes through. Okay, so the activity that is taking place is the load. The ticks, there is the measure of the delay time in terms of clock tick, where each tick is approximately 55 milliseconds. 55 milliseconds. Milli means times 10 to the power of minus 3. So 55 millisecond means 55 times 10 to the power of negative 3. So if you change the number, this will be 0.0055 seconds. This will be 0.0055 seconds. That's what we call the tick time. The tick time for in this regard. Now let's take a look at the route metrics. Still on the route metrics. Just now we're looking at the example, but now let's take a look at the route metrics itself. So one very big concept that we normally describe when we talk about route metrics is the administrative distance. Okay, the administrative distance. Administrative distance is what determines which type of the routing protocol that we will select. Which type of the dynamic routing protocol. It could be which type of dynamic routing protocol or which type of protocol in all that we're going to select. Okay, administrative distance is a fixture used by routing protocols to select the best path when more than one paths are available in our network. Okay, it's the features that we use to select the best path when more than one options are available. When more than one option for the data or data packets to go through are available, we use what we call the administrative distance. If the administrative distance is a huge number, then we're not going to use, we're not going to select that path. We're not going to select that path. If the administrative distance is a small number, then we select the path. Okay, so because the administrative distance is normally used to determine which path we follow. For example, let's take a look at a network. For example, let's assume there are two network routes. Okay, one is an OSPF route, the Open Shortest Path First routing protocol. This one, and the other one is Enhanced Interior Gateway Routing Protocol. Okay, this one. Let's say we have two paths to follow. A data packet has two paths to follow. Okay, we have two network routes to send a data packet. Now, how do we know which of these paths? One path has Open Shortest First Path Routing Protocol, and the other one has Enhanced Interior Gateway Routing Protocol. Now, how do we know which path to follow? That's where administrative distance comes into play. That's where administrative distance comes into play. So to know the path to follow, we have to look at the administrative distances. Okay, they are default, these are default values. They are calculated automatically by the system, by the protocol itself. Okay, so now let's assume that the open shortest path route has an administrative distance of 110. The open shortest path has an administrative distance of 110, while the enhanced interior gateway routing protocol has an administrative distance of 90. So which one are we going to choose? Which one is the system going to choose? The dynamic routing protocol the system will choose? The system will choose the one with the smaller administrative distance. Okay, the one with the smaller administrative distance is the path that the data packet ought to follow. Okay, meaning is the one that is freer for the data to go through. Is that okay? Okay, so the enhanced this one, enhanced interior gateway routing protocol, the enhanced interior gateway routing protocol will be selected as the preferred route. Yeah, we already mentioned that. This one will be selected as the preferred route because it has a lesser administrative distance. Now let's take a look at this table. See, this is connected 0. Static route is always 1. Yeah, it's always 1. EIGRO enhanced interior gateway routing protocol 80. Open shortest path first. Open shortest path first routing protocol is 110. Routing information protocol is 120. So the one that will be selected automatically is this one, the enhanced interior gateway routing protocol, because the administrative distance is smaller. So the one with the smaller administrative distance is usually the one that will be selected automatically or dynamically. Is that okay? Now let's move on. Dynamic routing protocol, still on it. We say there are two distinct type of dynamic routing protocol, which we've mentioned severally. Two distinct types of dynamic routing protocol. One is the distance vector, and the other one is the leak state routing protocol. Okay, the distance vector routing protocol and the leak state routing protocol. Now these protocols, we've already introduced them in section 9.2, right? Now the procedure for configuring the router using the routing information protocol version 2 of the dynamic routing protocol will be looked at in section 7, this chapter section 7. Okay, so we are still in section 3. When we get to section 7, we look at the routing information protocol version 2 and the configuration of this routing information protocol version 2 on the router. How is we configure the router? We look at it in section 7. Now let's take a look at the distance vector routing protocol, which is the first type of dynamic routing protocol. Number 1. We can call it number 1 in the dynamic routing protocol. The first type of dynamic routing protocol. Now the routing algorithm that periodically sends the entire routing table to its neighboring or adjacent router is called the distance vector. Okay, it's a routing algorithm. Okay, because every routing protocol is a routing algorithm. Okay, when you are defining a routing protocol, you can start with this. A routing protocol, every routing protocol is a routing algorithm, especially the dynamic one. Okay, especially the dynamic routing protocol. You know, okay, because they are automatic. Okay, so a distance vector protocol or a distance vector routing protocol is a routing algorithm that periodically, from time to time, okay, from time to time, that's the meaning of periodically, from time to time sends the entire routing table to its neighbor algorithm that from time to time sends its routing table to neighboring router or adjacent routers is what we call the distance vector routing protocol. When the neighboring routers receive the routing table, what would they do with it? Because we say a routing algorithm whereby from time to time a router sends the entire routing table to its neighboring router, right? A particular router sends its entire routing table to its neighboring router. That's what we call the distance vector routing protocol. Now, when the neighboring router receives the routing table, what will they do with it? It assigns a distance vector number to each route. That's what it does with it. It will assign a distance vector number to each route. It gives them number, maybe number 1, number 2, number 3, like that. It gives them a distance based on the distance. That's what we call the administrative distance. It gives them a distance vector number. Okay, so when the neighboring router or the adjacent router receives the routing table from the router that has broadcasted its algorithm, or the routing table on its algorithm, they will assign a vector number to each route. Now, the distance vector number is typically specified by some metrics, such as the hop count. How many hop counts did the packet follow, or the routing table follow before it gets to this router? So it usually assigned based on the number of hop count, which is the number of routers. Yes. So when we say hop counts is the number of routers the data must have passed through to reach the destination network. Okay. So this is what we call the distance vector routing protocol. A distance vector routing protocol is a routing protocol that usually has a routing algorithm that periodically sends its routing table to its neighboring router. It normally sends its routing table to periodically, constantly, a routing algorithm that normally has the ability to send its routing table to its neighboring router. And then we say when the neighboring router receives the routing table, what they do with it, they have to assign a distance vector number to each of the route. They have to assign a distance vector number to each of the route. Now, this distance vector number is typically specified by some metrics. And these metrics, one of the metrics they normally use is the hop count. Okay? And we already know what is a hop count, which means the number of routers that the data must have passed through, or the data packet must have passed through before it gets to its destination. Okay, so we have router A, router B, router C. Neighbor router is 0. This one, the neighbor router is 0, neighbor router is 0 for router C and router A. The hop counts are 0 because nothing has been sent. Hop counts is 0. Okay. So in a distance vector protocol, the router first determine its neighbors. That's the first thing it does. The router will determine, let's say we're looking at router B. It has to determine its neighbor. There's one adjacent neighbor here. There's also another adjacent neighbor here. Okay. The first thing this router has to do in a distance vector protocol, the router has to determine its neighbor or the adjacent routers. Either it determines its neighbor or what you call adjacent routers. All of the interconnecting routes will have a distance or a hop count of 0. Okay. All of the interconnecting routes, these routes, all of the interconnecting routes will have a distance or a hop count of 0, because the route itself has not reached any router. So the hop count will be 0 for this route, for routes. When you're looking at the route itself, this one, when you're looking at the route itself, the hop count will be 0. Hop count will be 1 when you've passed through one router. When you've passed through one router, then you have a hop count of 1. When you pass 2 routers, you have a hop count of 2. When you pass 3 routers, when the data pass 3 routers, it will have a hop count of 3. Right? Okay. Now, routers use the hop count matrix to determine the best route to forward a data packet. So if a router wants to forward a data packet, he has to look at the hop count matrix. How many hop count will this one, if we follow this way, how many hop count will it pass through before it reaches the destination? Assuming the destination is here. Okay, maybe from here to here is 1. Maybe there's another router here, another router here. So if here to here 1 hop count, 2, 3, okay, maybe 3 hop count before it reaches the destination for this one. But for this one, only 1 hop count. Only 1 hop count. So since this one has only 1 hop count, meaning we pass through one router, this router will forward this data through this side to the destination. We forward it through this side to the destination. Is that okay? Okay, so here, let's say we have router A. You can see the path, the subnet, the IP subnet is 10.10.200.0 between A and B, and between B and C is 10.10.150.0, and between C and D is 10.10.50.0. So for this one, hop count is 0 for A. Why? Because on up till it gets to this router, there is no hop count. It's when it passes this router, you have one hop count. So router B, I think this is an error. This is a B. Router B, when you now have 10.10.150.0, that's this place, you now have one hop count because it has passed through one router. Assuming you are coming from A, you are coming from here. Assuming you are coming from here, okay, when you pass this one, you already having one hop count. But before you get to this router, your hop count is 0. Your hop count is 0. But when you're here, because you've passed through one router, you now have a hop count of 1. Then when you are here now, you are going to this place, you have a hop count of 2 because you've passed through router 1, 2. You've passed these two router. If you are coming from here, if here is the home of the packet, if here is the home of the packet, and the data packet is coming from here, so when it passed through this one, it has one hop count. When it passed through this second router, it has 2 hop counts till it gets here. So that's why you see that when it has crossed here, when it's now on this place, it has 2 hop counts. It has a 2 hop count, 10.10.50.0. It now has a 2 hop count, as it means coming from A. Okay, A to B to C to D. Okay, so this is what is explained. This is what is shown in this table. These ones are B, okay, not A. This is B, this is C, router C. Okay, from A, the hop count is 0. When you are still on router A, the hop count is 0. When you are on router B now, or when you've passed through router B, and your IP subnet is 10.10.150.0, your hop count is now 1 because you've passed through one router. When you now on router C, or you pass through router C and your IP subnet is 10.10.50.0, you've passed through you now have 2 hop count because you passed through 2 routers. Okay, so now let's move on quickly. Distance vector protocols. In a distance vector protocol, each router determines its neighbor. Yeah, each router will determine its neighbors and build its list of neighboring routers, and then send a routing table to all the neighbors. Each router will determine its neighbor, build a list of all the neighboring routers. I mean, we list them, how many routers are my neighbors. You will list them, and then forward the routing table to all the neighboring routers. Then the neighbor routers update their routing table based on what they've received, the information that they've received from the determinant router. Now, when complete, each router's routing table provides the list of known routes within the network. Each router's routing table will give all the list of the known routes, all the routes that can be used within the network. Is that okay? Now let's take it. We've talked extensively on the distance vector routing protocol of a dynamic routing protocol. Now let's talk about the second type of dynamic routing protocol, which is the link state routing protocol. The link state routing protocol establishes a relationship. This one, a relationship has to be established. Establishes a relationship with a neighbor router, not just broadcast to all neighbors. It will establish a relationship with a neighbor router. Now, the routers exchange link state. The two routers, both the one that established the relationship and the one that received the relationship, both routers exchange link state advertisement. So they advertise. One, we advertise. Let's say router A, we advertise to B. So if B is free, B will acknowledge. We advertise, and the two routers exchange link state advertisement to update neighbors regarding route status. So to update themselves regarding route status. Okay, now the link state advertisements, that is between these two routers, where relationship has been established, are only sent if there is a change. These link state advertisements are only sent, not all the time, okay, not like distant vector. They are only sent if there is a change or loss in the network route. So if there is no loss in the network route, this is not necessary. If there is no change, except there is a change or there is a loss in the network route, and then the least state protocol converge to route selection quickly. So when there is a change, then the least state advertisement will be sent between two routers that have established relationship, and then they will converge to select which route is best for use. Now this is a distinct advantage that this link state has over the distance vector protocol. This is a distinct advantage, ability to establish a relationship with neighbor and also exchange link state advertisement with the neighbors, and then set up a route path. Okay, so this is the advantage that the link state has over a distance vector routing protocol. And in that case, that one exchange updated routing table at fixed time interval. You know, the distance vector routing protocol exchange updated routing table at fixed time interval, at every fixed time interval, periodically. That's why we say periodic. The distance vector routing protocol is very periodic, but this one is only when there is need, when there is a change or there is a loss of routing information. Okay, so, and you know the first one is slow, but the leak state is not, because it does not unnecessarily bug the entire system. In fact, the leak state routing protocols are replacing the distance vector protocol currently as it stands, because you can see the advantage, right? The advantage is clear, that it does not just broadcast advertisement. It does not just it has to establish a relationship, and the neighbor router that is available will link up, and then the link state advertisement will be sent and will be acknowledged, and if there is need be, the route will be selected. Okay, so it minimizes redundancy and every other thing that can set in to bring traffic on the network. So it reduces traffic and so on and so forth. So with this, we've come to the end of our today's class. Okay, thank you for joining us.